We'll dim the lights here in a sec and get going. Ooh, that's really dim. Can we get a little bit of light over the podium? Just a little more over the podium. I can't see the buttons on the remote. Hey! All right, welcome everyone to the Friday the 13th of February session of the Royal Astronomical Society of Canada, Ottawa chapter. We've got quite a good lineup here tonight, and we are switching things up, so do bear with us. Some things will not be in the sequence that you're used to, but that's okay. Special welcome to everyone here tonight, members and visitors both, as well as a special welcome to other RASC centers that might be tuning in or have members here. And of course, a welcome to everyone who's watching online this evening. There we go. Of course, as you know, this is our hybrid meeting format, online and in person. We are recording this webinar for posterity, and it's available at our website at ottawa.rasc.ca. For those of you online, please use the Q&A to ask a question to the speaker. Chat box comments will be seen by all, and raise your hand is disabled. The RASC Ottawa Centre acknowledges the trust placed in us by our First Nations with their ancestral lands and skies, which we get to enjoy. This evening's program, I'm Jonathan, and I'll be the host with the mostest this evening, followed by Dave Chisholm. We'll do Ottawa skies for February. We'll be doing the observation reports after that. Richard Taylor will then do the monthly observing challenges. Rick Wagner is going to do, is it Wagner or Wagner? Either. Okay. That's just good. Rick will be doing a two-part presentation on photometry with a break in the middle, and then we'll wrap up towards the end. Welcome to new members in January. We have a couple new members, two of them. Heather Ann Duguay, hopefully I'm pronouncing that right, and Deborah Kovac. Are they here tonight? Scream and yell if you are. No? Maybe they're online. Okay, Ottawa skies for February. Dave, over to you.
It's certainly been a marvelous winter for observing clouds. Anyway, so let's move on and see what we hopefully might be able to see in February. Because our meetings is a little bit later this month, unfortunately some of these things I'm going to tell you about have already happened. Particularly the moon phases. The full moon was on February the 1st. It was known as the snow moon by the early Indigenous folks, also known as the hunger moon. New moon is this coming Tuesday, the 17th, Shrove Tuesday. Get your pancakes. That's the night of the new moon. I'm bringing this up because our next meeting has been pushed out again, and so we do have a total lunar eclipse on March the 3rd. Don't get too excited about it. A reason being is that when it peaks is at 6:33 a.m. Sunrise is at 6:14 a.m. So not going to see a whole lot. You may, I think, certainly before the sunrise, you'll be able to see part of the eclipse. And but don't worry about that. The next full lunar eclipse is coming up soon on June the 25th, 2029. But actually, we do have a partial eclipse this year, August 27th and 28th. It's 93%, so it's a partial eclipse, but it's certainly, and it's at a decent time. It peaks at 12:12 a.m. So I would probably aim to go to that one versus the upcoming one on March the 3rd. And my slides aren't moving forward. There we go. That's me. This is the timing of it. This will all be in Astronotes, so you know when things are at. Sunrise, sunset. The days are obviously getting longer according to this. Mercury on the 19th, we had the greatest eastern elongation. That means it's the furthest away from the sun just after sunset. So you'll be able to see it. It looks like a little pinpoint of light. And either side of this date, you should be able to see Mercury in the evening sky. Venus is rising and setting with the sun this month, as is Mars. Jupiter is visible in the evening and through the night. And Saturn is visible in the early evening, so it's setting at probably about now. It's setting probably around 8 o'clock. So you got to get in there before 8 o'clock. Uranus is visible in the evening, and Neptune is visible in the early evening. And here is our cartoon of the month. In case you can't see the fine print, it says we'd like to study the effects of gravity, loud music, and beer on astrophysics. Thank you.
Thank you, Dave. I like that one. Okay, we're going to do our observation reports. And first up is Bob Olson. Are you here or are you online? It's so dark in here, I can't tell.
Is there any light on the podium at all? Yes,
Yeah, a little bit.
I don't. Chris will do it. You're going to flip the slides, Chris, please. This is about, holy mackerel, I can't see. Oh, here it is. 37 million miles distant and has a magnitude of 11. It should be visible with a mid-sized telescope. Next one, please. This galaxy is one of Richard's challenge objects. It's a Seyfert galaxy, which means that it has a giant supermassive black hole at its core, and thus is very active. The black hole has the same mass as 600 million suns. The galaxy is about 340 million light years distant, and the little spiral galaxy beside it is called NGC 6252. I believe that was also part of the challenge. Next, please. This image also contains many other galaxies. These are easier to see if I use software to remove the stars. Next image, please. And sometimes they are even easier to see if the image is inverted to a white background. So this is a pretty small field of view. A lot of galaxies. Okay, next image, please. This pretty open cluster is another challenge object. It's about 6,000 light years distant and lies above the plane of the galaxy. And thus, it has very little interaction with the other stars in the galaxy. It has survived far longer than most other open clusters. It is about 6.8 billion years old. This is 2.2 billion years longer than our own Earth. Next image, please. This interesting galaxy does indeed look like a fiddlehead. It is about 106 million light years distant and is nearly twice the diameter of our own Milky Way. Next image, please. This emission nebula reminds me of more of a tarantula than a Viking helmet. It is about 12,000 light years distant, and it started expanding 100 or to 200,000 years ago and has expanded to around 30 light years in size. The nebula is also being formed by the radiation of a Wolf Rayet star at its center. Next image, please. The designation NGC 2244 actually refers to the open cluster at the center of this image, rather than the Rosette Nebula surrounding it. The stars are 400,000 times brighter than our own sun, and 50 times as more massive. The stars in this bright don't last long, and this cluster is only 5 million years old. If you really want to photograph just the Rosette Nebula itself, you should really use a wider angle image. And hopefully we'll have more imaging to follow this month. Have a great day.
Thank you, Bob. Those are some great shots. Next up is it Bojan or Bojan? Bojan. Yes. All yours.
So I think Bob covered the majority of what the challenge objects were, and let me just figure out how to go back. Yeah. So this was the first one. I'm going to talk more about how I captured these photos because I think that's partially interesting too. So I am one of the fortunate owners of a telescope that is down in Texas in Starfront. So I'm not beholden to any of the weather challenges that we have. So when I want to observe, I just go up to my bedroom, to my office, sit down at the computer and observe, which is a lot easier. So this is taken with an Epsilon 130, which is a reflector at like f3 and a QHY 268 camera, and just 24 minutes of exposures, taken sometime in like mid-January, January 19th actually. So the pictures get taken all in Texas as I'm sitting at my computer, and then they stream back into this software in the bottom right called Lovell or something like that in the bottom right. And it just stacks the images using your GPU, and that's vastly faster than using PixInsight, which, for example, uses just your CPU. So when I tried to stack these in PixInsight, it took like an hour. With the GPU, it took about 10 seconds. So this is actually a picture of NGC 6251 and 6252, which was part of the challenge. But because the field of view is so large, where is it? I don't know. So this is a problem I struggle with in visual astronomy too. It's like, cool star field. I think I know what I'm looking at, but it'd be nice to know. So there's some software that is called, you've probably used this before, it's called astrometry.net, and you upload the frame that you took, and it uses plate solving and annotates your picture. So you just take your frame, you dump it in there, and it tells you exactly what you're looking at. So fun fact for this is I enjoy IT, I enjoy putting things together, so you can actually self-host this. So they give you a Docker container. So you run astrometry.net locally on your laptop. You don't need to actually have the internet when you're doing it, and you can annotate your own image. So these are the actual two galaxies that Bob showed that are tiny, but it was a confirmation that I was looking at the right thing. I have another presentation in April or May about Starfront, how I sent my gear down there, how I connect to it, and how many clear nights I get. So I'll talk about that then. Thank you.
Great, thank you, Boyan. So when it's cloudy here, can we all live at your house and use your telescope? All right, John Thompson, you're next. You know how to drive this thing, right?
I think so.
That's forward. And if you need to go back, that's back.
Oh, I was looking for the laser. Yeah.
Oh, yeah. Just don't point it at the audience.
Okay, this picture is sort of hot off the press. It was taken between 1:30 and 2 a.m. last night. About 2 weeks ago, I got word that there was an extragalactic supernova had been discovered in the Virgo cluster. Up until the past, I have seen two extragalactic supernovae, but they're relatively close ones. One was about 20 years ago in M81, the Bode galaxy, near the Big Dipper, and the other one, I believe, was in the Whirlpool galaxy about maybe 4 or 5 years ago. Both of those were relatively close galaxies, that maybe 50, 60 million light years away. Now, these galaxies are in the Virgo cluster, and there's actually two of them. Oops. That's not. Okay, I was trying to get the laser. Oh. Anyways, you see a faint one. Actually, three galaxies. There's a bright one, just bottom center. Fainter one is 4165. 4168 is the one lower, and then there's one off to the right. And that star right in the center of the frame is the supernova, which was discovered just less than a month ago, actually January 14th. And by February 1st or so, it had got up to magnitude 13.6, which sounds pretty faint, but for a supernova in the Virgo cluster, it's very bright. Most of them are 15th or fainter. but last night was the first chance I really had to get a snap of it. And the last information I saw said it was magnitude 14.7, but it looks brighter than that to me. But there are ways of doing photometry that using Cyril, which I haven't had a chance to use yet. I was doing it for the R Corona Borealis about a year ago, so I'll still try and get a magnitude for that. So there they are. This is a screen capture from Stellarium, which just shows the three of them. But you can see there's no supernova there. So it hasn't, I believe Stellarium does update some transient objects, but not this one so far. But those galaxies are on the order of over 100 million light years away. They're quite faint, like one, the brightest one is 11th magnitude, the other two are around 14th magnitude. And that, I forgot to mention, that was a 20-minute exposure using my C-star. And not very good skies. There was a lot of ice fog in the sky, so I was fortunate to be able to get that. But quite a thrill to get a supernova at that sort of distance, so like it's maybe 120 million light years. Okay?
Thank you.
That's very interesting, and thank you for the shot from last night. Supernovas are really cool. Okay, Paul, you're doing some aurora stuff, aren't you?
Thank you. Yeah, you got to take some when you get some. The skies certainly haven't been very giving this winter, especially since about November, actually. But we do have periodic treats of the aurora still. The cycle is still very active, still producing some amazing displays. The couple of the most recent ones, unfortunately, peaked at the time when it was daytime here, and folks in Europe got good views. Other times when they have peaked here, they had to battle with the cloud nebula, or the light pollution from the moon. But anyway, on January the 21st, I got a very short window. I had a heads up on the possibility of this, and as you can see from the chart here, the top right corner, the hemispheric power index, HPI, is a measure of the strength of the auroral display. And typically when it's quiet, it's down around 20 or 30 type of thing. I get excited when it starts to get around 70. So 140 went, okay, I got to get out and see this. But it was not a clear night. And I watched it for a while, and this is basically what I saw, like a diffuse green glow in the northern horizon with some hints of structure. And so I watched this for about half an hour or so, and I thought, well, it's not really doing much for us. And I was getting ready to pack it up when I noticed that it started to brighten up, and certainly the green layer started to get a bit beefier, and I could start to see some diffuse stuff above it in the red. And for about 10 minutes or 15 minutes only, where I actually had a sucker hole, it started to flare up, and it got quite interesting there with pillars going up to about 30 degrees, 35 degrees elevation. So that was very cool. But as I say, it was very, I could actually see the reds in that display, which is a little bit unusual. You know that they're putting out some power there if you can actually make the reds. It's certainly harder to see. But as I said, it only lasted for about 15 minutes. You could see rays moving from the east to the west as it progressed. And then it started to fade out, and it went back to that for the rest of the duration, which I didn't watch because then the clouds came in. So I got about 20 minutes, 25 minutes of good viewing of it, and certainly a few satisfying pictures. So January wasn't a total wash. And I think that's it for me. Thank you.
Thank you, Paul. Those are some great aurora shots. All right, Richard. I see movement, so he's here.
Okay, so these are my very few observations that I made this month. I did have one very, very nice night on February the 5th, so most of these pictures are from February 5th. And I wanted to try and get a picture of the Little Dipper hanging down from Polaris, but unfortunately I have trees on my northern horizon. So when it was hanging straight down, it was hidden in the trees. So I had to wait until, this was probably about 11 p.m., and by that time it had swung over to the east a bit more. And you can start to make out the stars of the Little Dipper here. So we have Polaris right there at the top, and then the handle of the Little Dipper coming down this way. And the two guardians of the pole here are pretty easy to spot in even Ottawa skies. But the other two stars are quite a lot fainter, more like magnitude 4 and 5. So you'll only see those if your conditions are very good. And there it is, more annotated so that you can see the pattern. Now this is a view of Polaris, quite a bit zoomed in. And if you're trying to do a polar alignment, you really have to be aware that Polaris, although it's the closest bright star to the North Pole, it's not actually at the North Pole. It's not directly above the axis of the Earth. It's a few minutes of arc away from that. So when you're aiming your polar axis of an equatorial telescope, if you have one of those telescopes that goes right in the polar axis of your mount, then you'll see a star field like this. And the idea is you have to put Polaris a little bit off center. Now the next picture, I've actually put some notes here. If you want to visually find the position of the pole, it kind of helps to look around Polaris and see this right-angled triangle of stars with Polaris at the right angle. And then there's a little trapezium hanging off this corner of the right-angled triangle. On the other side of Polaris from the right-angled triangle, there's a pair of stars here. And these ones and these ones actually point to the pole. So if we go back to this picture, that's what you'd be seeing in the telescope. You'd have to find this right-angled triangle, the trapezium, follow that line and that line to where they intersect. And there is the real North Pole. So that's something for you to think about when you're looking at the area around Polaris. Now, I'm very happy to see some other people had managed to take a picture of this. It actually turned out to be fairly challenging to find these objects, especially if you're using an equatorial mount, because when you're getting that close to the pole, it's what's called a mathematical singularity. And so any little change in direction makes a big effect on where the telescope is pointing. It turns out to be very, very tricky to aim an equatorial mount near to the pole. So this is the open cluster that is closest to the pole, and it was kind of tricky to find with the equatorial mount. So I cheated. I brought out my C-star and used it in alt-azimuth mode. And for alt-azimuth, meaning altitude and azimuth around horizontally, the singularity is straight up at the zenith, and Polaris is nicely placed at 45 degrees from our latitude here. So it was a piece of cake to find it and point in that direction to get a good picture of the Polarissima cluster. As usual, this is a stack of many 10-second exposures. Do I have it?
No, I'm sorry, I don't think I noted down how many pictures it took, but it's probably on the order of a couple of hundred pictures, and then it stacks them up. And I did do what's called a drizzling effect. I magnified the resolution to get the little tiny stars that make up this cluster to look at as pinpoints. And there's the two galaxies. 6251 is the brighter one, and 6252. This one, I did try and use my equatorial mount, and I had a great deal of difficulty. I nearly froze my fingers off trying to gradually move up the stars of the Little Dipper in order to point towards this, because the go-to function just would not work at all. So a very, very tricky target. And then I also suggested that you try and get some pictures of Jupiter, but as it turned out, the seeing was not the best for getting the details on Jupiter. However, again, on the 5th of February, I did manage to get this one. This is with my Schmidt-Cassegrain telescope with a Barlow lens, so I got a lot of magnification. And then I did manage to get the red spot as well as the cloud bands. And that little dot on the corner there is the moon Io. So those were the challenges for January. And Mark Lilienthal also got some very nice pictures online on the Discord server. Thank you for the other people who showed them tonight. That was wonderful. So what's up for the next month? Well, there's a very simple constellation called Canis Venatici, the hunting dogs, which is just below the handle of the Big Dipper here. So there's the Big Dipper handle, the bowl is up here, and underneath the handle, a little bit farther south, there is this pair of stars. Now, Cor Carelli, the brightest of the stars, is quite a bright star. It's as bright as some of the stars in the bowl of the Big Dipper, so you should have no trouble spotting that one. The other one is not quite so bright. I think it's about magnitude 3, but it's all by itself out there. There's not many other stars of the same brightness in that area. So it's not a difficult constellation to see if you can get a nice view to the northeast. Now, this constellation does have quite a few showcase objects in it, and it's a fairly large area of the sky which is designated as part of this constellation, even though there aren't very many bright stars. But this is a nice place to find some wonderful galaxies. So the other challenge objects for this month are the Whirlpool Galaxy. Now, it's much easier to find if you start from the Big Dipper here, but it's between the Big Dipper's, the end of the Big Dipper's handle and Cor Carelli. And the Whirlpool Galaxy is a wonderful thing to take photographs of. It's a spiral galaxy with an elliptical galaxy off to one side, and it comes out very beautifully. It's not as impressive in the eyepiece because it is, a face-on spiral, so a bit faint. A better one for binoculars is M106 up here, which is a more tilted spiral galaxy, somewhat in the same orientation as the Andromeda Galaxy. Not as big, but it's a fairly sizable object and fairly bright, so you should be able to spot that one in binoculars from a dark sky. And then for the really challenging object, there's another pair of galaxies right down here, almost on the line between the two stars making up Canis Venatici. And these ones are kind of unusual because they're a bit distorted. They only have one main spiral arm. So they may be a little bit like that Fiddlehead galaxy that Bob Olson showed earlier. So see if you can find these ones for the month. For the solar system challenge this month, Dave mentioned that the new moon is on February 17th, but the very next day, a one-day moon, a very, very thin crescent moon, is going to be very, very close to Mercury just after sunset. So if we do get a clear night, fingers crossed, take a look in the west just after the sun is set, and if you can spot the moon, there'll be a bright star nearby. It's not a star, it's Mercury. And again, Dave mentioned that Mercury is approaching its greatest elongation, its greatest separation from the sun. So this is your chance, if you haven't already, to see Mercury. And the moon kind of forms a signpost to be able to find it. And then, of course, if you're up at 5 in the morning on the March 3rd, there's also that eclipse of the moon, too. So there's your challenges for the month. Thank you very much.
Thank you very much, Richard. And we're going to go right now into our main presentation for the evening. So, Mr. Wagner, over to you. Do you know how to work this thing?
No.
Okay. So green arrow is forward. There's a small red arrow for backwards, and there's a little button here if you want to use the laser pointer. Just make sure you point at the screen. Okay.
Good. All right. Well, good evening, everybody. Thank you for being here. It's lovely to have a chance to talk to you on a formal basis rather than just observations. So many of you will remember the few times I do talk about observations, it's often to do with photometry. I measure the brightness of variable stars, and I do quite a lot of that. And so I thought it's about time I told you basically what I'm actually doing. So, first, why would we want to measure, for instance, variable stars? Why do we want to measure the brightness? The primary ones that I'm interested in are called pulsating variables. So it's a, back laser, there we go. So this is, you can see this one, it's getting bigger and smaller. In fact, if you were actually to look at a real star, it would also be getting hotter and cooler as it did so. But you notice that it's not always expanding out to the same size and shrinking down to the same size. So this is actually a multi-periodic star that's probably pulsating in two separate frequencies at the same time. These are what are called non-radial pulsations. The surface is still moving in and out, but in fact, a star like this, I'm not really familiar with these in depth, but these pulsations would actually appear to rotate around, so it would be more like waves moving around the star. So in effect, they're like non-radial. They're more around the surface. This guy, I don't know what that one's doing. But there are modes like this, and if you get really extreme, for instance, you can get thousands of modes like this multiplying and all operating at the same time. And so, for instance, looking at the sun, you can do helioseismology where you've actually got, thousands of different frequencies all pulsating on the sun at the same time. All of these things are very critically dependent on the interior structure of the star. So another type of variable star that a lot of people like is the eclipsing binary. So here we've got two stars. One is a larger, cooler star and a smaller, brighter star orbiting around each other. I don't know why they've got a string connected to them. They don't use string, they use gravity. But they do go around each other, and as each star goes in front of the other one, of course, the brightness of the system drops. Because, of course, these are so far away, we can't actually see the individual stars. What's interesting about these is as we measure the light curve, the amount of time that a star spends in eclipse as it goes across, or as the other one goes across in front of it, is related to its size. We can also measure these in different colors. So for instance, a blue filter and a green filter, and use the difference in the magnitudes to come up with the temperatures of the two stars. If you have a big telescope, you can do radial velocity measurements. So they do spectroscopy of the two stars. They can determine how fast they're moving towards and away from us as they go around each other. Now we have all the information we need to find out exactly how big each star is, what temperature it is, and once we know that, we know how much energy each one is actually radiating. So now we know how bright these stars actually are, and by comparing that with how bright they appear to be from the Earth, we can tell how far they are. And actually they've used, you take a dozen or so of these, for instance, in the Large Magellanic Cloud, and by averaging the results together and stuff, you can actually measure the distance to the LMC to within about 1%. Another one that's quite exciting, these are cataclysmic variables. So this is, we have a compact object, in this case a white dwarf at the center, with a larger star. This can be a main sequence star, a giant star, supergiant star. And the white dwarf's galaxy is enough to actually suck material off the larger star. It goes into an accretion disk, swirls around rapidly, scrubbing against itself as it goes, heating up to actually millions of degrees. So you actually get an X-ray emission. You get a bright spot here where the stream impacts on the disk. You can also get light from the larger red star, though generally that is much fainter than the whole rest of the system. And as these things go, there's instabilities develop in the disk. You get flickering of this bright spot as there, clumps come off the other star. So there's all kinds of interesting things. And then they go into outburst every so often, and they get 6 to 8 magnitudes brighter, and then they pop along with like about an hour period stuff, only a couple hundredths of a magnitude, but it's all critical to the scale of the system, the orbit times, and all that kind of thing. So we can do the pulsating stars, gives us information on stellar structure by looking at the changes in the light curve of a pulsating star. You can actually detect the evolution of a star. It's as its interior structure and elemental abundance changes, its period changes, and you can actually detect, stars evolve on a scale of millions of years. So over a period of 10 or 20 years to be able to actually detect the evolution of a star is exciting. A lot of the stars are Lyrae stars, for instance, are a pulsating star with a period sort of around 6 to 8 hours, and they all have approximately the same brightness. So that means that we know how bright they actually are by measuring their apparent brightness. We know how far they are. So now we can follow them out through the galactic halo because they tend to be in a large sphere around the galaxy. So now we're developing knowledge about the galactic structure. You can use other stars to, for instance, map out where the galactic arms are, how far they are, and so forth. The Cepheid variables are probably the most famous pulsating stars, and those are the ones that actually tell us initially told us the distance to other galaxies. And by connecting the Cepheids in a galaxy with a supernova in the same galaxy, now we know how bright a type 1a supernova is, and we can measure the distance to galaxies back like a billion light years. So now we can actually start to measure the evolution of the universe. We learned it was expanding, and now we know, for instance, that the expansion seems to be accelerating. What else could we do? Exoplanets, a little planet going around its star. If its orbital plane points at us. The planet goes in front of the star, dims the star by 1% or so, a lot of them a lot less. By timing very accurately that passage of the planet across the star, you can look at changes in its orbital period. You can possibly detect moons around the planet or other planets in the system. And finally, something I've tried a couple of times, you can measure asteroids, the brightness of asteroids. Generally, they're all potato-shaped. So as they point end on, for instance, they're dimmer than when they're side on. So you can measure their rotation period, which gives you some indication possibly as to how they're made up. And also by watching them as the Earth sweeps by them and they fall behind us, you do imaging and photometry through several months, you can actually work out the approximate shape of an asteroid. So, why us? Why should we do this? Well, there's too many targets. The AAVSO keeps a database, the American Association of Variable Star Observers keeps a database of, hopefully, all known variable stars. There are currently 15.5 million in their database. The Zwicky Transient Facility, if you remember the old 48-inch Ocean-Schmidt telescope at Palomar, they've equipped it with a huge CCD camera array, and it images huge amounts of the night sky every night. They actually capture as many as 1 million transient objects every night, things that are moving or changing in brightness. And a professional can follow up maybe 10 to 15 of those. So the other rest of the million are up to amateurs. The Vera Rubin telescope coming online now is expected to find 10 million transients every night. Many targets the professionals can't deal with. The Vera Rubin telescope, for instance, saturates at 16th magnitude. You need a 24-inch telescope to even see a 16th magnitude star, and it's already too bright for them to measure the photometry. Things like the Vera Rubin, the Zwicky Transient Facility, Assassin, all image on a sort of a daily to weekly basis. So a star that's varying on a period of a couple of hours, they only get a data point every 5, 6, 10, 20 periods. So they can't get well-defined periods and light curves out of them. And even Vera Rubin is only going to last 5 or 10 years at the most. If you want a century of data, you go to the amateurs. Go to the AAVSO, look at SS Cygni is a star. They've got data going back to the early 1900s. And frankly, some professionals just aren't very good photometrists. We can do better if we work hard at it. So back to the basics, the magnitude scale. Originally started off with the Greek astronomer Hipparchus, who basically just classified the stars. He looked at sort of the brightest 20 or so stars and said, those are stars of the first magnitude. And then he counted down till the 6th magnitude stars were just basically the faintest ones he could see. So my analogy for that is actors and actresses and stuff. Ian McKellen and Sir Derek Jacobi, those are actors of the first magnitude. Adam Sandler and Will Ferrell are dim bulbs of the 6th magnitude. I always get a boo from somebody. So Ptolemy, about 2 centuries later, actually started to refine this by watching as stars appeared as twilight deepened. So the first magnitude stars were the first ones to come out, then the 2nd magnitude and so forth. So kind of a little more of a measurement idea on it. 1721 or so, Halley started thinking about, we should be measuring these things, and he estimated that the difference between a 1st magnitude star and a 6th magnitude star was probably something about a factor of 100 in brightness. How he figured that out, I have no idea. But in the mid-1800s, Norman Pogson actually decided that's approximately correct. And so he defined that 5 magnitudes should be a factor of 100 in brightness. So it's what's called a logarithmic scale. You can see, too many buttons. If you divide the flux of one star by the flux of the other, take the log, multiply by 2.5, and you have a minus, because why is a magnitude 1 star brighter than a 6? 6 should be, it's bigger than 1, but it's astronomers. So anyway, so what you end up with is a 1 magnitude difference is a 2.512 times change in brightness. So you can use that quickly to judge brightness variations. 2.5 for 1 magnitude times 2.5 is 6 for 2 magnitudes, 15 for 3 magnitudes, 40 for 4 magnitudes, and exactly 100 for 5 magnitudes. And then you can just keep multiplying it out if you end up with something like comparing the sun to a 6th magnitude star or something. So the photometry, this is really brief history of photometry. Back in the mid-1800s, they actually started trying to measure stars. It was all done visually, comparing, putting stars in order and things. So really, how they actually got ratios in brightness, I don't know. But back in the late 1800s, early 1900s was when things like the British Astronomical Association, the Germans, and the Americans started forming organizations to collect visual estimates. So that's the way they started, looking through a telescope, looking with your naked eye. You're comparing a star to nearby stars with a known magnitude. So it's called differential photometry. It's a difference between 2 stars. They're really rough. Somebody who's really good at this can get about 1/10 of a magnitude. Most people, it's probably more like 0.2 or even as bad as 0.3. Amazingly, the human eye is actually about 10% quantum efficient. So 1 out of every 10 photons actually has an impact on your eye and is detectable. So I said we're comparing our target star against stars of known magnitude, so we need to find stars of known magnitude. So this is the chart. We go to the AVSO and we tell them we want to observe T Corobor, T Corona Borealis, which is this nova that's been supposed to explode for a year, 2 years now, and hasn't done anything. So when I go there, I get my chart, and you can see this is my target star here, and then the magnitudes of various stars in the field. They've all been measured quite carefully. They're all indicated without a decimal point, so that we don't think there's extra stars in there. And the ones I've been using are the 98, 102, 106, and 107. And so what I do is when I get out to the telescope, I take my chart and I orient it so that it matches the orientation of the view in my telescope. And there's the view through my telescope. This is a very nice color image from friend Malcolm Park in Kingston. So you can see there's T Corona Borealis, there's the 9.8, the 102, the 106, the 107, that's a 112. So if we go back, see, I tried to superimpose them. But anyway, so this morning at 6 o'clock I was out and I looked, and I decided that the star was about 1/4 of the way in brightness between the 106 and the 102. So if it's 1/4 of the way in brightness between 6 and 2, that's a +1, so I got 10.5. And that's basically all there is to visual observing. They did do a lot of work in the late 1800s with visual photometers, and they actually got really good using prisms and stuff, so they could use polarization to dim another star down to the same brightness as your target star and stuff. So they could get down to about a 20th of a magnitude. One of the big problems with this technique is there's no permanent record. You pick the wrong star when you're looking through your telescope. There's no way to tell after the fact, other than the fact that your magnitude is wrong and different from everybody else's. So you got to get it right. So in the late 1800s, somebody developed photography, and the astronomers were right onto that. And it was used for about 100 years. Problems, very low quantum efficiency. Only 1% of the photons actually do anything. They're not very linear. They have a limited dynamic range, so you can only measure really accurately stars over a range of perhaps 3 magnitudes. And probably sort of a 1/10 of a magnitude accuracy. You do have a permanent record. You can go back after the fact and look at it again. Did I, maybe this star is varying or it's the wrong color. I can go back, I can measure different stars. And one of the best examples of the permanent record is the digital access to a sky century at Harvard. They took these almost 600,000 glass plates at Harvard College Observatory and ran them all through a huge digitizer. And now you can go online and look at any of these images. So this is, these are actually photographs of some of the images. So you can see, I know everybody's immediately saying, there's the lagoon, there's the Trifid, there's M24 up there. It looks like somebody has rather inaccurately marked the center of the galaxy. But you can see, and from the scale of this, I'm guessing this was the 10-inch Bruce camera. Very nice image, considering this is 100 years old. This is actually probably my favorite photograph of all time. So you can see this is the Andromeda galaxy. And these are actually Edwin Hubble's notes. They write on the back side of the plate, not the emulsion side. And he's marking he's marking novae that have appeared in the galaxy, except that you see that this one he's crossed out. It's not a nova. This is a variable star. This is the first time a Cepheid has been detected in another galaxy. And it's the one thing that finally proved that the Andromeda galaxy is a galaxy on its own, separate from our galaxy. And previously, there were people said, well, no, these are spiral nebulae, like planetary systems forming or something in our galaxy. And I was down in Harvard College Observatory and got to see this plate in real life. It was, and it inspired me to actually try and photograph it. And I've now done about 50 estimates, measured magnitudes for that star. It's about 19.8 to 20th magnitude. So from then, about the 1950s, we started getting into what's called photoelectric photometry, and it was popular, meaning almost nobody did it, but because it's difficult. So for about 40 years, uses photomultiplier tubes. There have been some use of photodiodes, but they're not nearly as sensitive, so it doesn't tend to be as useful. Works well enough on bright stars, and it's a lot easier to build the equipment. So this was the workhorse, the 1P21 photomultiplier tube, and it's just like, your old classic radio tubes in an old radio. And the way they worked was high voltage, a couple of thousand volts, and a photon from our star would come in here and hit a photocathode right there. So what would happen is it would knock off an electron, and because of the magnetic fields and the electric fields in the tube, the electron would swing over here and be accelerated and smack into this thing fairly hard, the next dynode, and maybe knock off 10 electrodes. And they would rush over here, knock off 100, 1,000, 10,000, 100,000, 1 million, 10 million, and eventually you get a little pulse of current out on the anode. And it's a really little pulse of current. So you have to have fancy amplifiers to measure it. And basically, if you're looking at a star with your telescope, you get this little teeny current, you run it through a voltmeter, and you measure what the current is, and then you do that for various stars. Or if you're lucky and good, you get fast electronics, you can actually measure every pulse, and you do actually photon counting. So here's an example of an actual photomultiplier photometer. Your F10, because you do this on a Schmidt-Cassegrain, and the light cone comes in here, it goes through one of the colored photometric filters, and it comes to here, there's a little metal disc with an aperture in it, little hole, 1 millimeter in diameter, 1 millimeter standard, it says. On your 8-inch telescope, that's about 100 arc seconds in diameter. So the light goes through that hole, this little lens images it as a fairly good-sized spot. You don't want too detailed, gives you better noise characteristics and so forth. But anyway, then out comes the signal, goes through these amplifiers and everything. So, very good precision. You can get better than 1/100th of a magnitude. Slow, man, 1 star at a time. So here's our picture. This is what we see in our telescope. Now, I should mention, here, there's a flip mirror. So we can flip a mirror in here so that we can have a crosshair so we know exactly where this thing is pointing. So there's our view through the telescope with the flip mirror. And what we do is we put in our green photometric filter, we center the aperture on T Corona Borealis, and we read our voltage meter or use a chart recorder perhaps, and say for 10 seconds, 20 seconds, we measure and take a note, write down the voltage, or the current rather, in our notebook. Now, of course, in that aperture there's skylight, light pollution, other garbage that we don't want. So what we do is we pop the telescope aside a little bit and image an empty spot of sky. At least we hope it's empty. You can see there's actually a very, very faint star in there, so it's biasing our skylight reading. But anyway, we don't know about that. So we read our current again for 20 seconds. Then we move it over, we center it on our comparison star. This is our 9.8 magnitude star that I pointed out. Watch it for 20 seconds, take another reading, write it in our notebook. Now we have to do what's called the comp star, or a check star rather. So we center it again very carefully. If you don't center it right, some of the light gets cut off by the aperture and your reading is wrong. So you have to do this very carefully. Then if you want to do it also in a B filter, a blue filter, you go through the whole process all over again. Then you can't just do one reading. Suppose there was a little bit of cloud coming through. So you do the whole mess over again, maybe 5 times to give you 5 different readings. Then you do all the calculations to figure out what the magnitudes are. If you pick the wrong star, there's no permanent record. If the star is slightly out of the aperture, so you're not getting all the light, if there's a faint star or galaxy in your sky area, or another faint star in with one of those stars, your readings are wrong. You have no permanent record. How do you know what went wrong? All you know is if you're lucky, you know that your readings are different than other people's. One thing, though, that's very interesting about them is they can be very high speed. Very slow and very high speed at the same time. Because they are reading continuously, if you've ever watched the moon occult a star, it just winks out instantaneously to your eye. Put a photoelectric photometer on a good-sized telescope and you can actually watch the diffraction pattern as the star disappears behind the edge of the moon. You can measure the diameter of a star as it goes behind the moon. So you can do very high-speed work with it.
All right, everyone, we'll get going here. And Rick Wagner will be coming back to continue his presentation on photometry. So thank you.
Okay, so everybody rested and ready for lap 2. I'm not getting slides moving here. Oh, benefits. I guess you're back on.
So we're just going to take a slight detour before we get into the second part of Rick's presentation. I'm going to talk about benefits of being a member, of which there are quite a few. So for those of you who do come out on a regular basis and you're thinking about membership, this is what it's all about. The greatest part of the membership is the group you have together with you, both the people here, the people online. It's a great bunch of people with a lot of expertise in a lot of different areas. And all the way from beginner astronomers, I'm fairly amateur, to some people here who are really quite talented. And so being able to connect with them and look at the stars with them and learn from them, it's a really great community. We have a number of other things that are available. The Ted Bean Loan Library, which is a telescope library, which is kind of a cool thing, especially for people who are looking at buying their first telescope or putting some money into something maybe it's a little more expensive than what they've got now. The Ted Bean Loan Library gives you the opportunity to sign out a telescope and try it out. And we've got quite a range of telescopes, and I believe we have 1 or 2 C-Stars now, which are the new digital telescopes, which are really quite something. We have the Stan Mott Library. Estelle recently retired as our librarian for a very long time, and I believe there's a couple people that are potentially volunteering to take her place, but we have quite an extensive library of books and material that can really help you along your journey becoming an astronomer. And of course, the Fred Lossing Observatory at the Mill of Kintail Conservation Area near Almont. And it's been around for quite a while. I remember going there when I was 17 years old, and I'll be 60 tomorrow. So it's been around for a while. No, none of that. We have 3 large telescopes out there, and another member who's proficient on the telescope will train you on how to use it if you're interested. And as well, we have a setups with power, so you can bring your own equipment along, and we do little star parties once a month and stuff like that. Astronotes, monthly, we put out our Astronotes. There's the Journal of Astronomy that comes out from RASC itself, as well as every year you're going to get the Observer's Handbook, and that's what it looks like for 2026, and that's a really great compendium of everything you're ever going to want as a reference as you become a more proficient astronomer. Our Ottawa Discord server is quite active with the members. You saw some great images here tonight. You should see what's on the Discord server that members are putting up on a regular basis. And a lot of the communications, tips, and stuff back and forth, you'll see that all on the Discord server, as well as in some of our Google email groups and stuff like that. We also get the Astrospheric, that's a mouthful, Pro Access. That's a $65 value right there, but that's to help with weather forecasting, so you don't have to all go and live at Boyan's house and use his telescope. Membership, regular membership for an adult is $118 a year, which, if you've been out for dinner lately, that's one dinner out. Family membership, $112.50, plus then $18 for each adult in the family, $10.50 for the youth. And a youth membership, if you're under 21 years old, or under 25 if you're a student, is $77.40. So great value. All right. Rick, I think you can come back now.
Okay, so when I left off, now that you're rested and ready to go, when I left off, we finished with basically the historical side of things. Now we're into array detectors. So if you can imagine, the photoelectric photometer was essentially like a 1-pixel camera. Now we have an array of up to, say, 50 gigapixel cameras, 100 gigapixel cameras. In the amateur world, something 20 to 50 is probably about 20 to 50 megapixels is about as big as we get. CCDs started becoming common in the 90s, and nowadays, because of the scale of manufacturing, CMOS cameras are basically taking their place for most amateurs. Digital sensors with high quantum efficiency, some of them get up over 95%, which means almost every single photon shows up in your image. They're digital sensors, so you get a handful and you get an array of numbers. You don't have to measure and calculate and mess about. Very linear response over quite a wide dynamic range. You can measure the brightness of stars over 5 or 6 magnitudes in a single image. When you take an image, all the stars get measured at the same instant. The photoelectric photometer, I'm measuring one star, a cloud comes in, I measure the comparison star. What's the good of that? In this case, all the stars, generally we're doing a small frame of, small angle of view, so all the stars are basically treated the same by the clouds, the light pollution, the time, and everything. You can get high precision. I've had runs where the consistency of my stars is a thousandth of a magnitude, and you have a permanent record, so you can go back and check things. So, 2 different ways to do this. One is called all-sky photometry. Some people call it absolute photometry, and basically, this is how you would figure out how you would measure those known comparison stars in a field. So you would pick, say, T-Core Bohr. I don't know the magnitudes of the stars around it, so I would image standard fields that have been measured by the professionals, and I would measure those over the sky, and then I would measure my field, and then I would measure the standard fields again and measure my star field, and do that a bunch of times. And then you do fitting and correlation and all kinds of fancy stuff. Why? Because the atmospheric conditions vary with time and space. The extinction, as a star gets closer to the horizon, it gets dimmer and dimmer. If you watch a sunset, the sun doesn't just get dimmer, it gets redder. So if you have 2 stars, a red star and a blue star setting towards the horizon, the blue star is going to dim faster than the red star. So you can't compare them anymore. Air glow, if you ever see time lapses, you'll see waves of pale green floating across the sky. And of course, clouds. Everybody complains about clouds. One of the nice things about photometry is even with some cloud, I can observe. I was observing all night last night. I should say my telescopes were observing all night last night, in spite of the fact that there was thin cloud going through, and the data all looks great. As I said, you have to image a whole bunch of standard fields. There's a lot of math involved, and you have to have excellent atmospheric conditions. In an area like this, you might get 3 or 4 or 5 nights a year when the conditions are good enough to do this kind of photometry. So instead we do differential photometry. We measure the difference between a target star and a star of known magnitude. We measure the variable star against a comparison star, and then we measure the check star. There it is again, I'll get back to it. You measure the check star against the comparison star. Because we're doing a small field, because the image all happened at the same time, there's no chance for atmospheric effects to change with time or change very much over our field of view. So the photometry workflow, we shoot a whole bunch of images. We calibrate the images, we apply a bias, dark, and flat field. The imaging, even the pretty picture guys can tell you all about doing that. Star detection, it's easy to look at an image and see where the stars are, but it's nice to have the computer do it for you. Aperture placement, I'll get into that later again. Flux extraction, how much signal is there in each of these stars? Then we do the differential magnitude calculation, and we generate a light curve. So what does all that mean? Well, the flux extraction, we want to measure how much signal there is in various stars in the image. Star is basically a point, almost like an infinitely small point source of light, and it's light, when it comes through the telescope, comes through the atmosphere, it gets spread into a blob. So we've got a point spread into a blob. There's a function that describes the shape of that blob. Difference imaging, really cool. Aperture photometry, nice and easy and well done with amateur equipment. So the point spread function, what we do is we pick half a dozen stars in the image that are isolated and moderately bright. We make sure they're not saturated, and we decide what's the shape of a star. Like it's a little bump in the signal, so it might be a Gaussian, for instance. And we fit a model to a bunch of those stars. We average it out. So now we know what the shape of a star is. We take that model and we plunk it on all the other stars that we're interested in, and we scale it up and down till it matches the star. And by knowing how we've scaled it, we know how bright the star is. It's difficult, it's computationally expensive. You have to have good optics because you want the stars to be pretty close to exactly the same shape over the whole field of view. You need excellent tracking. You can't have oval stars. I mean, you can get away with it somewhat, but ideally not. Its main use is when you're in crowded fields. You've got stars that are too close together. You can't fully resolve them. So like a globular cluster, or if there's a star with a very near companion. They use it a lot in space telescopes and dense star fields. Difference imaging, I think, is really cool. What you do is you take your telescope, you take hundreds and hundreds and hundreds of images of your field, you take all the absolute best images, the sharpest images you've got, you add them, stack them all together, and get the perfect image of your field. Now, every image that you want to measure is going to be blurrier than that image. So you can take that image, blur it slightly to match your science image, subtract it. If nothing in the field has changed, you get 0. There's nothing left. If one of the stars in the field has gotten slightly brighter, when you subtract the reference image off, there will be a little bit of signal left where that star was. If a star's gotten dimmer, you will actually end up with a little negative hole where that star was. And what's really nice about this is it can detect quite small changes down to 1/100th of a magnitude or better. And you can actually do it in places where you can't hope to resolve the stars. For instance, in the core of a globular cluster where there are hundreds, thousands of stars all crammed in, even though they're blurred all together in your picture, all of them, they all disappear except for the variable star. It just ends up left as a little bump or a little hole. They use this OGLE, is the optical gravity lensing experiment, which was basically point a telescope at the hub of the galaxy and measure like several million stars in every single image. And I mean, you know, if you take pictures of the center of the galaxy, it's a mess of stars. So what we do is we do aperture photometry. It gets back to what I said about photoelectric photometry. We have an aperture. Here we're going to use a virtual aperture on a digital image. Now we're going to try and measure the brightness of stars to 1/100th of a magnitude or better. So having a chart that has magnitudes to 1/10th of a magnitude isn't going to be very useful. So I go back to the AVSO and I get a photometric table. So this is all the stars in my field that were labeled as a 9, 8, 102, 106. This is more accurate magnitudes. So for instance, my 9.98 star, we can see is actually a 9.809 in V. That's V for visual. It's the green photometric filter with an accuracy of about 0.023. Generally, these things are around a few hundredths of a magnitude accuracy. And there's the 102, 106, 107. So there's all the stars I've been using for most of my observing. So I take a picture of the field. This is one of my pictures. And you can see there's T Corbor and some of the comparison stars around. And what I've done is I've opened it up in a program called Astroimaging J. Most of them work relatively similarly. And I click on the star. And first thing it does, let's go to the next image, it's zoomed in. And you can see it's put a little green aperture around the star. And what it's going to do is it's going to measure how much signal there is inside that aperture. Now what's interesting is that because we're doing this on an image, we don't have to worry about, oh, maybe the star's dragging a little bit outside of the image. We put the aperture where the star is. It's probably 10 arc seconds in diameter instead of 100, so there's like 1% as much skylight getting into that. Do we measure the skylight that's coming in there? Yeah, we do. It automatically puts in this annulus around the star, and what it does is it measures the brightness of all the pixels in that ring. That's the background, the sky background. We call it a background, it's really mostly foreground. But even better, suppose there's a faint star. Remember on photoelectric photometry, if there was a faint star in there, I don't know about it, and it's going to mess up my readings. In this case, the computer looks at all of the pixel values in there, looks at the statistics and says, oh, well, these pixels don't seem to match the statistics of a regular background, so we will just ignore those. So all these white pixels in here, it's basically said, those are suspicious pixels, I'm not going to use those. So we've already refined the estimate of what the background is. The other nice thing is because it surrounds the star, it means if there's a gradient across the field, for instance, it's brighter on one side than the other because of the moon, that gets averaged out nicely. So then I just go over and I choose what my comparison star is going to be, and I do exactly the same thing. I just click on it. It puts on the aperture. It puts on the annulus. It tells me what the signal is in the star. Then I tell it that's my 9.8 star. It's at 9.809 magnitude. And it immediately tells me, oh, well then T Corbor is at 9.963. Here's my comp star, and it's at 11.055, or check star rather. What the heck is a check star? If you imagine if you were a carpenter and you're trying to measure the length of a board, and you've got your new assistant, young guy down there who's on his phone, right? And you're out here trying to measure this end of the board, and he takes the other end of the tape measure, and he's kind of, while he's on his phone, waggling it back and forth. You're not going to get a good reading. It's exactly the same thing here. What happens if the star that I've chosen as a comp star is actually varying? It means I'm measuring relative to something that's going up and down. So my star, my target star, I'm not going to get good estimates of it. So what I do is I have a second star, which is the check star. And if I measure the brightness of this relative to this, and it stays constant, then I know both stars are constant. If it varies, then either this one is varying or this one is varying. Now I know I got a problem. I can switch one of them out. Try it again. I've got a permanent record. I can just go out and measure a different star. So I've done that. Now I tell AstroImage-J, I say, save the positions of these stars and their magnitudes, or the comparison star, and the positions of the three stars. And then I hand it 1,000 images and I say, do the photometry. And in 2 minutes, it's measured all 1,000 images, measured the accuracies, the positions of the stars, the sizes of the stars, the focus, the brightness of the background, the relative magnitudes of the stars, all kinds of stuff. And it's all done based on one image. And again, if I don't like the results, I can choose different stars. I can pick a different star in here. Oh, I discovered, oh, there's another variable star in the field. I can just click on it and do photometry 1,000 times on another star in the same field. So, once we've done all that, we want to put up a light curve, magnitude versus time. we show the variable and we show the comparison star so that we can see that the check star doesn't vary, the variable star does, and we highlight the variability. Well, this doesn't show up very well. But this is UY camelopardalis, and you can see there's my measurements of the star. These are really old ones from back 2011 to 2014. But you can see that over that period of time, so this is each night, it takes like 8 hours to go through a cycle. So every time I figure out the phase and I map them over top of each other, phasing, and so all the observations all line up into a nice curve. You can see this is a classic RR Lyrae star, steep rise to brightness and then a slower decrease. And along here is a haze of my check stars. And you can see they're fairly constant, a little bit of scatter, but basically constant. So I'm happy with my comp star. So there's always going to be problems in this kind of things, error and noise. One of the earliest problems you run into is when you're buying your equipment is sampling. When you have this is particularly bad for CCD cameras, but even some of the early CMOS cameras, you have all your little pixels that are light sensitive. The electronics that read those out and that create the pixels and everything are all in front of the pixels, and they're opaque. So not the whole area of each pixel is actually light sensitive. So we have a situation here where there's gaps that don't accept light. So if I have largish pixels and very small stars, you can see I collect all the light from this star. I'm probably missing 40% of the light because it's falling on the electronics here. And this one, I bet I'm not getting 40% of the light. So the same star in different places on the chip is going to give me different readings. So we want to make sure the image of our stars is big enough to cover a bunch of pixels and fix that problem. The cameras, you can saturate a camera. They aren't perfectly linear. This is a test of the SBIG camera that we had on the RASC remote telescope for a while. And you can see that as we increase the exposure from 0 to 100, man, that looks pretty nice and linear. Until you hit 65,000 when it just stops. What's 65,000? It's 2 to the 16th. It's a 16-bit camera. So 65,535 is the biggest number it can send out. And that's when it stops. So if you have a star that actually goes brighter than that, it gets to a certain point and then it just stops recording information. Now, if we look at that in detail, you can see this is, if it was perfectly linear, this would all be along the 0 line. But you can see that from about maybe 7 or 8 seconds up to 80 some seconds, it's well within 1% of linearity. But then again, it drops off really bad. So if we were going to image with this camera, we would make sure we don't exceed the 65,000 limit on the camera. Atmospheric transmission, I've mentioned it a number of times. Bulk transmission, in other words, it dims things, but it also changes the colors. Blue light is extracted more than red light. It twinkles. The stars twinkle. Even in a telescope, if you do a short exposure, you will actually find you can measure the twinkling. You need to keep exposures longer than probably 10 seconds, otherwise you get starting to get scatter. And of course, clouds do come through and change things. One of the nice things about differential photometry is suppose a star comes in and cuts out 50% of the light. Well, a star that's twice as bright as another one, if you've got half as much light, it's still twice as bright as your comparison star. So you lose your signal to noise ratio somewhat, but it doesn't change your magnitudes. So I can observe on nights that pretty picture people won't do it. The camera sensors are all different. The filters that we use are all different. And you need to take that into account. Ideally, you should take that into account. A lot of people don't, but it means there's a lot of scatter between observers. You have to do your bias dark and flat frames correctly, or you can mess up your images. If you have a camera, we're not too bad down here at low altitudes, but like the remote telescope was up at 5,000 feet or something, and big chip, you would get a lot of cosmic rays. You could see streaks across where a cosmic ray had gone through the camera. And most cameras have hot pixels, and if one of those is in your star, it'll screw up your measurements. Difficult situations, if you have a bright star, it'll saturate your camera. So what do? You can shorten the exposure, but then you can start you will end up with scintillation. So you get a lot more scatter. So what you do, for instance, is you might take 2-second exposures or 1-second exposures, but do 100 of them or 1,000 of them, and then either stack them all together or measure them all separately and then average the numbers together. Another thing you can do is defocus. The trouble with defocusing is your star gets bigger and you can run into close companions. If a star has a nearby star, you defocus, it's more likely to run into it, and you're going to start measuring the other star as well. And even if you're sharply focused, there are stars up there with companions that are, there's a nice pair of Cepheids that are nice, they're bright, and they're easy to find because they're in an open cluster, and almost nobody's ever observed them because they're only 2 arc seconds apart. So only in the best images can you actually separate them, unless you're doing point spread function, which you could do. Meridian flips, if you have a German equatorial mount, you're observing, and then all of a sudden the mount flips upside down, and now your camera's rotated 180 degrees. And if your flats aren't good, you watch your measurements go along, and then suddenly, boing, and they're doing a different number, which is kind of nice because it does tell you that your flats are bad. Software tools, Aperture Photometry tool is a freebie that you can download. Gives you really cool information. It's really focused on 1, 2, or 3 images at a time, but it gives you like profiles of your stars, magnitudes. It can do photometry and all kinds of neat stuff. So it's good for looking at stuff in detail, learning about the stars in the images. AstroImage-J is free. It's really powerful. It's actually focused on exoplanets. So once you've done all your measurements, for instance, it can detrend, you know, if as the star's been rising, the star, you know, everything's getting a little brighter, it'll take that out, flatten it out, it'll calculate a model to fit the transit, it'll determine the start and end times and all kinds of cool stuff. But it's also very good at just doing basic photometry. Lev Photometry is by a guy, Pierre de Pontière, who's in Belgium. And he writes it, basically he's an advanced amateur astronomer, and it's just his toy that he keeps going, very powerful. Again, you input a bunch of stars, you tell it, you know, here's my target, here's my comp stars, my check star, and then you just hand it thousands and thousands of images. I know a friend of mine has done 3.5 million observations using Lev photometry. ASTAP is a astrometry, so it's measuring the image to determine the RA and DEC of everything in the image, and it does stacking, but it will also do photometry. Cyril, primarily image stacking for pretty pictures. It will also do photometry. I haven't tried it. Forenso is just relatively new on the market. It's a commercial package, but it's like 50 or 60 bucks by a guy, another one in Belgium. What's with Belgium? Really good program. It will go out and find comparison stars for you. It will find all the variable stars in your images. It's an amazing program. It only runs on Windows, so I don't do it. Maxim DL, written by Doug George, one of our members. Much more expensive, but also much more capable. It will do the photometry. It'll also control your observatory cameras, telescopes, filter wheels, cloud sensors, schedule observations, all that kind of stuff. And then if you really want to get into it, like I do, you roll your own. Python, there are amazing libraries out there of functions. AstroPy, PhotUtils will do all the photometry stuff. It'll find stars, measure them, and do all sorts of correlations and neat stuff. Light curve will analyze your light curves, find periods, find the shape, all kinds of stuff. But hundreds of hours of work putting it all together, at least for me. I'm an incompetent programmer. I think that about covers it. Do we have any questions? Andrea? Huh? I get overexcited.
I have 2 questions, yes. So first of all, can you tell me what telescope and which camera you use? And if somebody wanted to start doing photometry, what star would you recommend we start looking at?
Okay, well, I have 2 telescopes that I use all the time. One is the 16-inch Boltwood telescope that Paul Boltwood made with a QSI CCD camera on it. And it's in a roll-off roof observatory. Then I have a 10-inch Schmidt-Newtonian. Don't really recommend the optical system. It's not a great telescope, but I got it for $200. So I live with it, and it works. It works fine. And I also have a Takahashi 90 millimeter Apo refractor that I use, but it's on a portable mount, so I have to lug it out every time I use it. I think for the beginning photometrist, you want something that's moderately bright, say 11th, 12th magnitude. I like stuff that varies a lot. So you get something like an eclipsing binary that's got a period of 3 or 4 hours. It's going boing, boing, boing. So, you know, you can observe it for 2 hours and see a dramatic change. Or high amplitude delta Scutis, also a period of an hour and a half, 2 hours. And they're relatively bright. So, you know, you can get a nice, really nice looking light curve in just a few hours. We're working on, I'm in a working group with the AAVSO to try and do photometry with smart telescopes. And there's no reason you can't. I mean, there are people who are using C-star 50s and stuff for photometry. So that's probably the easiest way to start. And you just treat it like another telescope. The only trouble with it is that it has pretty picture filters, which are not the same as the photometric filters. So they're not, you know, it's not ideal, but a lot of people do photometry with DSLRs and color cameras too. So it's still interesting information, especially if you're doing something like eclipsing binaries. If you're looking for changes in the period, you want to know what time it reached minimum. And what time it reached minimum doesn't really depend on the color. So if you're using the wrong filters, you still get the same time, and it's still useful scientific information.
Other questions from the audience? Oh, I see a hand over here. Well, just hang on a sec. We got 2. I'm going to start down here, and then I'll come up.
Well, thank you, Rick. That was a very interesting presentation and a lot of information. Is it going to be in Astronauts?
I had not planned on it, but...
it would be nice to have something like that list of the software.
Yeah.
Would be very useful to have as a reference item. The other thing is that I have just begun trying some photometry with PixInsight. They have come out fairly recently with a package to do it, and it's linked with the AAVSO maps and so on. But I ran into a problem with Myra in Cetus. Very large variation in brightness and nothing around it to use as a comparison. What do you do when there isn't another nearby star of a similar magnitude?
Yeah, that's If you're using CCDs, you can try using fainter stars that are in the immediate vicinity. Because they're linear over such a large range, it will work. Now the trouble is that the signal to noise ratio, the accuracy to which you measure your comparison stars, they're much fainter, so you get much less accuracy. So what you can do, for instance, is maybe use a dozen of them. And so you compensate for their dimness by using a lot of them. The only other thing I can say is use a bigger field of view. Like a lot of people, for instance, would do MIRA with a DSLR and a short telephoto, say. Not really. I mean, there you're starting to get into the all sky type thing where, you're measuring the target star on one image and comparison stars on another. The atmospherics, may be different. They may not be at the same elevation anymore. So it does add complications.
Thank you. We have another question up here.
Thank you, Rick. Very clear. Sort of.
Okay.
You're one of the old folks that did everything in the past, and now you're still doing everything in terms of the observations and the reduction and so on. Do you find in the groups that you're associated with, do you find that you're starting to get a division of responsibility where you have people that get the images and they just send the images off to somebody else to let them do all the number crunching?
No, that may be coming, because one of the things we're looking at with the SmartScope working group is the trouble is that for instance, I might shoot 500 images in a night. So for me, uploading a couple of gigabytes of images, I mean, it's impossible. It would literally take days. I wouldn't be able to keep up with my imaging. So what we're going to do in the SmartScope field is hopefully we'll have a piece of software that will analyze your image, or it just measures all the stars in the image, where they are and their signal level, and then you upload that. It's a text file, so it's much, much smaller. And then software at the AVSO, for instance, would correlate, figure out which stars are which in the catalog, figure out what their magnitudes are, and do all that kind of stuff. So essentially in that situation, yes, the observer takes the pictures and then washes their hands of the whole thing. There are people who are writing software like Lev Photometry and stuff, and Forenso. So to that extent, yeah, they're taking the grunt work out of the photometry. But generally, most people are. In fact, some people are very concerned that if I'm not analyzing the images and measuring, I'm not here to just take pictures. So they're very concerned about their future.
Thank you. We have another question from the audience.
Hi, Rick. Yeah, I enjoyed that. Does the AAVSO have a tutorial for people wanting to get into this type of thing so that you can start in at ground zero?
Yes, they do.
Yep.
They have, in fact, they have several. They have ones for visual observing, because there's still people who do a lot of visual observing, which can be very useful. For instance, T-Corbor, I observe it visually. Every morning that it's clear, I've done about 350 visual observations of it so far, and about 8,300 photometry, like with the telescope. So, there's a balance there. But the thing is that to look at T-Corbor, it's 10th magnitude versus 2nd magnitude. That's all you really need to know at the most basic level. So there's visual observing tutorial. There's the beginners. I think it's a 10-star tutorial where you can go and it will tell you how to do basic photometry. The trouble is a lot of their documentation, for instance, is the CCD manual, which is like a 60 or 70 page manual that goes, I mean, it goes whole hog into all the details and stuff. So one of the other things we're doing on the working group is, you know, here's a 3-pager on how to get started. So.
Thank you. We got one more question from the audience, and then we'll check for questions online.
Rick, that was fascinating stuff and a great deal of work. You started out by asking the question, why do it? Because here's my question to you. What have either you or others done with this data that you've put so much work into getting? What kind of issues has it actually been applied to, your data yourself?
Me personally, one of the nice things they do, well, I submit all my data, or a lot of it, to the AAVSO. They have a database of observations. I think they're up to like 40 million or something observations now. And research scientists can go and download it and use it for teaching. People can use it for planning observations. They can use it for research and so forth. And every week I get an email from the AAVSO saying, you know, somebody downloaded so many observations of this star for this purpose, and I get a list. And in an average week, there are probably anywhere from 50 to 70,000 of my observations downloaded. So there are people using it. I was working with a researcher at the Los Alamos National Laboratory. She and a grad student were doing numerical modeling of high-amplitude delta Scuti stars. And I provided all the data on 4 multi-periodic heads stars that they used in their modeling efforts. And I had a grad student, PhD student from Japan, used a bunch of my data for his thesis. So it does get used.
Good stuff. Chris, do we have any questions online? No. Okay, I'll just ask the audience here if there's any more questions before we move on. No? Rick, thank you so much for taking a very advanced topic.
Thank you very much.
And presenting it in a clear, concise, and very informative manner.
Not
Thank you
very
again.
concise. Thank you.
All right. Speaking of our loan library, Estelle, after many years, retired from taking care of the library, and many thanks to Estelle. She worked at it so hard for a very long time. We are looking for a member to pick up the torch from Estelle and carry on with the library, and we're very open to that. So if anyone is interested, oh, Paul's waving at me.
Just a slight correction, actual slight update. We have 2 members that expressed interest in that position. They approached me last month, and Estelle gave them the tour today. So I haven't had, this is very, very fresh news, so I haven't had an update from those folks yet there, but I think our positions are filled, and what we were looking at, what I was suggesting is because 2 people expressed interest in this, you can do kind of like what Jonathan and I do with the MC position, where we can back each other up if we know somebody's sick or going on vacation. I've got to talk to you about that, by the way. Then you've got a backup person there to take the reins there. So I think that's what we'll be looking at. I won't name names right now because they haven't yayed or nayed me yet, but both of them have experience with libraries and library sciences. And so I think we may see a bit of a shakeup in how our Astro Library operates. So stay tuned. I'll give you the details as soon as I confirm them up.
Thank you, Paul. Okay, the Fred Lossing Observatory. A few more pictures here. I talked about it earlier. We've got 3 large telescopes out there, and we do monthly star parties, weather permitting. It's been very cloudy this year. It's been a tough year for that, but hopefully it'll be better in the spring and summer. All right, the next star party is scheduled for tomorrow. Is that correct? I guess so. Okay, so weather permitting, the next Star Party for members at the Fred Lossing Observatory is tomorrow night. Bring your date. Club information, the flow director is Rick Scholes. As Paul just mentioned, we may have 2 new librarians. The Ted Bean Equipment Loan Library is Peter Schut. If you need his contact info, reach out to any of us on the council and we can give you the contact info. We do have an open position for coffee and conversation, so if anyone wants to pilot a coffee maker, hey, let us know. And membership info, Art Fraser. Tonight in the audience, 40 here in person, 32 on Zoom for a total of 72 participating. Organizers and speakers, there's the list. You've heard them all tonight, and a big thank you again to all the speakers. Thank you. And a big thank you, of course, to our hosts, RASC National Office, and for providing us with Zoom. And any comments, ideas, send to meetingchair@ottawa.rasc.ca, and that's Paul with myself assisting. And as you've seen, we are playing around with the format a little bit, see how it works. And so if you've got any comments on that, do let us know as well. All right, next meeting. It looks like it shifted to the next Friday, the 13th. Part of what this is the Artemis launch, and the museum, of course, is very excited about humanity returning to the moon, and so they're having a big party if Artemis launches on the first Friday. So we've shifted to next Friday, March 13th, because we know no one's going to try and go to the moon on a Friday the 13th, right? So it'll be 7:30 at this location. Any observations? If you're interested in presenting, you've got ideas for future talks, please reach out to the meeting chair address below. Just a reminder, as you exit, the RASC Museum is closed. And just for your knowledge, if you are driving home tonight, there is a forecast for a little bit later on for the potential freezing rain. So just drive safe and get home carefully. Thank you. All right, post-meeting, for those who do want to go to the post-meeting after-party party, it's at Liam McGuire's on 1705 Saint Laurent Boulevard at Innis. And that's it for our February meeting. Thank you, everyone, for coming out. Safe drive home. Look forward to seeing you next month.